Okay, so today we're going to find the area between two curves, between F and G. So I'm looking from A all the way to B. And so I'm looking to find, there's my little rectangle. There's lots of little rectangles all the way across. And so now it's in terms of dx. In order to find the area of this rectangle, well, the area, I'm going to add up all the rectangles from A to B. And my base is d of x. My height, though, is this distance here. And this distance, it messes people up a little bit because I know this area here is negative, that's positive. But I'm not doing that. I'm looking for the area between two functions now. And so if you consider this area here is all, this area here, this area here fits really nicely. Now, it doesn't change if I move it above the x-axis or if I move it below the x-axis. It's still the same area, and it has a positive value. It doesn't matter where it is. And so I'm concerned with this height, and that height is purely going to be the upper function f of x minus g of x. So it's the upper minus the lower, and that's the area between two functions. That's what I do, upper minus lower. So let's try an example. Given sine x and x cubed minus x, sketch the two functions and find the point of intersection. Well, let me make a quick little graph here. And I've already been on my calculator, so if I zoom to number 4, here's sine x, here's x cubed minus x. As you can see, I've entered it. And so when I look at this graph, if I'm going to do a quick little sketch, I know it's going to be like this and like this. So in order to do this, I need to find this point, and this point. Using my calculator, I'm going to find the intersections. 5, 1. The first intersection point here is 0, 0. Find the next one. And I'm going to store this value. If I go here, x is there. I'm going to store that into A. Actually, I'll make, hold on. I'm going to store that into alpha B. Oh, one more time, there we go. Store this answer into alpha B. So I know that this value here on the end is 1.317616. The final answer has to be good to 3 significant figures, so I keep the significant lots of decimals here. Similarly, I'm going to also have that one on the other end, and I get intersection. It's the negative version of the same answer. So I can take x. I'll try and do this better this time. I'm going to take my answer, and I'm going to store it into alpha A. And there I get the negative version of the same point. So if I'm going to find the areas, well, I could go, if this is A, B, and C, I could go from A to C. The upper curve is g of x, and my blue curve is f of x. So it's the upper curve, x cubed minus x, minus the lower curve of sine of x, dx. I'm going to take that and then add it onto from C to B of, again, it's going to be sine of x, though, minus x cubed, careful your parentheses, minus x dx. Add those up and it will work. But there's also another way I could consider doing this. I know that sine is perfectly symmetrical about the origin, as is x cubed minus x. And so this area is congruent to that area. So I only need to find the area once and then multiply it by 2. So I'm going to find the area from my negative 1.31716 to 0 of my top function g of x minus my bottom function f of x. I've already been using my calculus, so let's continue doing that. If I remember, y1, this is y1, f of x is y1, and this is y2. So from here, I know this is y1 and y2. And so if I go to math, number 9, I'm going to go from alpha a to 0. Oh. And when I do that, I'm going to do y2, which is alpha y2 minus alpha trace y1. And I'm going to do that d of x. Enter. Now this is my final answer. Oh, and then I'm going to take it and multiply by 2 because there's 2 parts of it. And this final answer has to be correct to 3 significant figures. So keep your decimals as you go. The alpha a is a neat little trick for that. So there is our area between the 2 functions. Another scenario here. We want to find the area that's bounded by this function and the line y equals x minus 1. So if I'm going to do that, well, the x minus 1 is easy. It's this one here that's a little trickier. What I do know, though, y is equal to plus or minus the square root of 2x plus 6. It's 2 functions. So if I do this, I can say square root of 2x plus 6. And then the final one will just be minus alpha y2. All right, and so now if I graph it, there's my line, there's the first part, here's my second part. I'm looking for that entire area. And let me change my window a bit and make the maximum up to 8, I think will be nice. No, not quite high enough. Okay, so I'm going to make a sketch of this. Oh, I'm hitting my x maximum, not my y maximum. That's why I'm not seeing the graph very well. Let me try this again. Let me change my window. I can put this back to being 4. And it's my y maximum. I'm going to make that up to 10. 10. Graph that. Here's the first part. There's the second part, and I still need to adjust. Maximum 6. Here's my line, my curve. We'll do it in purple. Is somewhere like that. And so I need to find the area between these two. Well, I have this all the way up to here, and then it switches functions. I have 2 parts. I have to break it up. And so I need to find this point of intersection and that point of intersection. So going to my calculator, find the intersection, and we will get the value, 5, 4, that's convenient, 5, 4. If we do this bottom value here, and I could do it also by setting them equal to each, or plugging this into here by substitution and solving, but this is just faster. want. Here's the first curve. Find the second curve. I want it to be the other function, this one here, my second curve. I'm looking for my answer, and this one here is -1, 2. So in order to integrate this, I'm going to do this first part here. I'm going to do this part in here, these ones. So it's going to be from, oh, I also need this value here, but I know it's 3 just from transformations. I'll double, I know it's 3 negative. You can use your calculator to check it if you want. But I'm going to go from -3 to -1, and that will get me this area here to -1. The upper curve, which is positive 2x plus 6, minus the negative part, which is a lower curve, dx. And so if I do that, it should work out. That's the first part, A. I have to add it to this purple part here. Well, that's going to be from -1 all the way to 5. My upper curve is the root of 2x plus 6 minus x minus 1 dx. This is my computation to find the two. I have to break up in 2 parts because I'll call that B. I add them together and it works out nice. I'm not going to do this. You can save it for yourself. But what's important is the idea behind it. Your calculator will do it for you. But there's another way we can do it. A second method. So if we think about our graph, we have this. We have this graph, and I know I have a line here. And when I start to sketch it, I know I have something like this. I was looking at it this way, but how about if I take my rectangles and I go in this direction? Everywhere I draw a rectangle, it's the same curve in terms of dy. So I know that this value was -1, -2. This value is 5, 4. So if I do it in terms of dy, I know I'm going to go from -2 to +4. As opposed to the upper minus lower, it's the right curve. In terms of y, this is x is equal to y plus 1. So I have y plus 1 minus y squared. Let's solve here, and I get y squared minus 6 over 2 equals x. And so it's y squared minus 6 over 2 dy. And then I can do this computation, and it's much simpler. I know before I do it, I'm going to simplify, minus 1/2 y squared plus 3 dy, which is 4 to minus 2. Just rearranging it and collecting like terms, I get plus 4 dy, and now I can start to integrate. Y cubed minus 1/6 plus 1/2 y squared plus 4 to the y from -2 to 4. I'm going to leave it here. You can finish it off yourself. So lots of good ideas in here. I have my area between the curve, and it's always the upper minus the lower. That's if it's in terms of dx. Or you could also do the right minus the left if it's in terms of dy. Think about which combination is the better approach and go for it.